Hello, everyone. Welcome back to Build Your Own Large Language Model workshop. We're going to be in our second section right now called Reverse Engineering LLMs. And our goal for this section is to get a roadmap for how to build large language models we just don't know. So in our previous module, what we saw is running GPT-2 inside of a Colab notebook. And maybe the key insight here is that we could probably figure out from that in-memory model how to build structure our workshop today. So maybe we could do something to like reverse engineer that model and get a lot of the runtime components, at least the inference time components, from that model. So how would we do that? Here on the left, we've got an example. It says print model. So all we're going to do is call the print method on the model. And then there's a bunch of words that happen here. I think we should review those words very, very carefully and see maybe they give us a hint as to what we need for our workshop. So again, all we're doing here is reverse engineering the GPT-2 model to figure out what inference time components we need in order to build a GPT-2 style transformer, which seems pretty straightforward. Great. So let's just jump straight into code. And again, like we've seen Colab notebooks in the past, so I'm not going to necessarily run you through these again. We click connect, we click run all. Oh my gosh, great. I've already done that, so you don't have to wait with me. So the first thing we're going to do is we're going to load GPT-2 right here. And then I'm going to say, that we just have the model here. So like the whole thing is loaded. And then first thing I'm going to do is I'm going to try and print out the total number of parameters. What's a parameter? I don't even know right now. Maybe when we learn about perceptrons, we learn about parameters. But for now, let's think of it as a unit of size for a model. And GPT-2 small came out at about 124 million. Is 124 million a lot? It's more than a few million, and it's a lot less than a few billions. That's kind of the order of magnitude that we want to think about. But yes, it's very small based on modern standards. It's roughly the size of a small test. Great. So now we have the model in memory. Can I just call print model on it? Yes, I can. And then we see a bunch of words here. I am not going to explain what the words mean, but I'm going to highlight the words that we saw. And then we're going to explain them later on in future sections. So what are some words we're seeing here? We're seeing the word transformer. That's a real interesting word for those of us who know a little bit about large language models. Words like embedding. We see words like dropout and layer norm and linear here in the base. And we see a word here that's dropout again, and new glue activation. I say glue because I think it's funny. You think you're supposed to pronounce it glue or galu, something like that. I say glue because I think it's funny. We have dropout here, so on. Okay, so we saw a bunch of words. I don't know what those words mean. Maybe we'll see them again in a moment. Let's try and use something called torch info and call the summary method. Very similar to just calling print, just like a little bit nicer. So what's obvious from this? We have very similar blocks to before, but now we see GPT-2 block repeats itself 12 times. That's really interesting. We learned that there's 12 layers or 12 GPT blocks within a transformer. We just learned something really interesting. Great. And that kind of gives us the math of how we got to the number of parameters we had earlier. And the difference between 124 million and 163 million is whether or not you count the embeddings, which we do. In this one example, we will count the embeddings. Okay, great. So now I know stuff. I've printed out some words. I've called print. I've called summary. Let's try and reverse engineer the modules we just saw. We're just going to print them out in pretty print here to make it easier to read. These are the words we saw earlier. It's conv1d and dropout, embedding, and attention. Oh, attention. And layer norm and linears and glue activation. Wow, it's all of that stuff we saw a moment ago. Just a nicer list. Let's throw that into a graph. This is just me trying to render the graph in a way that makes sense to me. The hierarchy starts kind of making sense to me now. So there's this thing called the model, and it's got a transformer inside. Inside of it, there's embeddings and dropouts and module list layers. And these layers repeat themselves 12 times. And inside of them, there's something called an attention. Inside of them, there's something called an MLP. What's an attention? What's an MLP? We don't know yet. Great. Inside of those, there's dropout, conv1d, glue activation, layer norm, so on and so forth. Great. So let's try and take those words we just saw a moment ago and try and attribute them to something that looks like a roadmap for us to reverse engineer and like learn concepts. So, okay, we learned the word transformer. So that's going to be section 18. We have to really build up to get there. We saw the word embedding. That's section 16. We saw dropout. That's a part of section 13. These are all sections we're going to be working on in our workshop. We saw layer norm. That's going to become part of normalization. We kind of intuitive on something called residuals. We need those as well. We saw normalization. We heard the word MLP. That's a fun word. We're going to spend a lot of our second module learning the basics of machine learning, building up to learning about MLPs and feed-forward networks. We saw glue activation. That's going to be almost our next section, not the next section, but the next section. So we're going to talk about a lot of activation functions. Okay, so is there something beyond this little tree that is now a lot more visual and it's got more colors? There's also something called functions. Those are invisible in the module tree. We don't need to know why or what the difference is. So there's a lot of functions being called as part of our model, but when we kind of pretty print them, what we get to is there's activation functions, initialization, really interesting. We also have normalization, and then we see something called softmax. So that's section 14. Okay, so really cool. We learned about, we have a lot more sections that we're going to have to cover than we would normally have to cover, right? Like, because now we have softmax and embeddings and all of that stuff. Let's try and throw that into a tree just so we can understand what the function tree looks like. Oh my God, an entire transformer is just a bunch of functions being called over and over and over again. Transformer, MLP, transformer, attention MLP, attention MLP, attention MLP, attention MLP, attention MLP. Oh my God, we're calling these 12 times. We're going to scroll to the bottom and then we get to the end of this. Okay, so what we did, we'll just learn a large language model is a bunch of functions. Really cool. So let's print out the architecture. This is an exercise for you. Go to Hugging Face. And choose a text generation model, and then maybe a small one so we could load it into a GPU, about let's say 6 billion, maybe 12 billion model, maybe no more than 32 billion. We're going to have to start some problems to load them. So let's say I go here and I try and choose one of these models. 1 second, I'm going to scroll back down. And then ideally for us, we probably want to run these in PyTorch as well. And there's a couple of models here. Let's say I want to load up Tiny Llama. That's just the name of a smaller llama style model, 1.1 billion parameters, so about 5 times bigger than 10 times bigger than the model we're working on right now, GPT-2 small. And then I'm going to just give it the name, and I'm going to just load it like we saw a second ago. I'm going to go print, and I'm going to click summary. And then now we get to see a totally different model than GPT-2. This is Llama model. Wow, what does it have? It has attention layers like we saw a moment ago, and it has embedding layers, and it has linear layers, and it still has an MLP, and it still has an attention layer. Really cool. Has a RMS norm. What's an RMS norm? I don't know. A rotary embedding, positional embedding. That's going to be real important when we get to section 14, I think, 15. Great. So now you can go and choose any model from here and try and copy the name into your code block and then see if you can't print that model. I think that's going to be a real fun exercise for you to feel empowered. Great. So we did that. That's the code for this. And then we reverse engineered our roadmap for the day. So we have activation functions and transformers and dropout, which is regularization, and residuals and attention and normalization. And now we get kind of getting very close to having a roadmap for the day. But a lot of these are part of the architecture of large language models, but they're not the foundational buildings to how to train a large language model. So for that, we need a couple more things. And before we get to that, I actually want to talk a little bit about ablation tests. Here you got to see a GIF from the Voyager TV show from Star Trek, and you could see the ablative armor on Voyager. Why is that cool? Because I thought so. But ablation armor gives the starship protection, and in a similar way, ablation tests give machine learning engineers protection. Not clear. What does the word ablation mean? It means to take away, and that kind of gets into why do we use any of these components? So you just saw a bunch of components and you're like, is that the only way to build a model? Why do we use those models? And the answer is, and I love this quote from CS336, Machine learning is an empirical field. That means we use the components that work. The components we use are the components we use because they outperform the components we chose to not use. So the reverse engineering that we just did for GPT-2 is actually super meaningful because it told us these are the components that worked back when 2019 was happening when they wrote that paper. So really cool. We just learned about ablation test. An ablation test is just means taking something away, comparing how the system works. If it works better with it than without it, it won the ablation test. Great. So a couple more quotes while I'm quoting people here, and I love quoting people. Chris Olah in 2020 said, LLMs are grown, not built. LLMs are grown, not built. We are going to build up the architecture, but the large language model learns the language itself. We don't have like language specific things for the most part happening here. We're not going to teach about subjects and verbs and all of the fun linguistic concepts. We're just going to show it the English language and it's going to pick up all of that by itself. So Karpathy has this really other great quote that he says, which large language models is kind of like summoning ghosts. We show it the entire English language and its foggy recollection of it is what it learns. So I really also love that metaphor, and I think it's important to keep those two metaphors in mind. Where in my third metaphor, I'm going to include myself in this very august set of quotes. I probably shouldn't, is something like farmers build the farm, but the tomatoes do the growing, right? You could set up trussels, but the tomatoes actually climb on top of the trussels and make the tomatoes grow. Really important. We're not doing the growing. We're letting the LLMs do the growing, like Chris Olah says. Okay, great. So now we talked about ablation test. So now here's our full roadmap. We mentioned here are all the components under the architecture that we mentioned earlier. We also have MLP and feed-forward networks. We have activation functions, and we have a bunch of concepts that we're going to need to learn to just train a model. So this is roughly our roadmap that we reverse engineered partially from GPT-2. And the stuff we didn't reverse engineer is stuff we just need in order to build a machine learning model or a large language model. Okay, so now we have this full roadmap. There's a lot of words you don't know here. We're in section 2 right now, by the way, reverse engineering LLMs. I want to show you this because I think it is going to help make a lot of things land. Every single section really has roughly a line of code, a few lines of code, a paragraph of code worth of deliverables. And that is roughly it, right? So in section 1, we saw model.generate, and we now know how to call, how to use an autoregressive loop on a model. We know that we can reverse engineer large language models by calling print and summary on them. All of that stuff's super cool. Every one of the next sections can really be summarized in like a line of code. We're going to spend like 20 minutes per section or more. I don't know how long this recorded version versus the in-person version is going to be, but it's about 20 to 30 minutes per section. Every one of those can be summarized in one line of code. If you just want the lines of code, here you go. They're in front of you. You have the script from code-0, go Justin Angelo AI/code 0. You could just have these lines of code. Our goal for the day is to learn what these lines of codes mean. So we have an intuitive grasp on them as we're building large language models. A lot of our sections are going to have external demos in them. For example, and I'll learn more about section. This is one of my favorite ones. I forget his name. I think it's Sean. I'm so sorry, I forgot his name. But it has this 3D really great model here that has all of the components we saw, but in fun linear algebra form. Why linear algebra? You don't know the answer to that yet. You're going to find out in section 6. Hint, hint. But for now, you could just see all of these embeddings and the layer norm and the MLPs and the softmax. What's a softmax? I don't know. And you can actually just run these, which I think is really, really cool. I think there's a skip button that I could click and then it runs. It's really fun. You could see attention going through all of these various layers. We can even take a set from our tiny sample model here, Nano GPT, 80,000 parameters, to GPT-2 Small, 124 million parameters we saw earlier, and we can deep dive into each of them. Oh my goodness, I could really deep dive into this and see this MLP block. How cool is that? Okay, great. So now we have this demo, and I really recommend you spend some time here. But you could also use it to run through and see all the calculations happen in real time, which I really think is a useful thing to do. There's also all of the list of models here. There's Nano GPT, GPT-2, GPT-2X extra large. You can see it's much larger. And GPT-3, you could try and call print and summary on those. That'll be a fun exercise for you as well once you've looked at the demos. Great. So our next section is going to be about perceptrons. What are perceptrons? Perceptrons are the basic unit of work within a deep neural network, or any neural network, really. So I hope to see you back. We're going to build up from perceptrons to activation functions to GPU performance, back to MLPs, which we saw as a real component we need to build large language models. Then we're going to go into loss functions and backpropagations, which is how we train machine learning models. That's going to be a big section, a big module that we're going to be working on today. Thank you so much. I hope to see you in the next section.